Hello everybody, welcome to today's webinar, Ford 6.7 Failures and Fixes. I am Amanda Harmoning. I am an admin assistant here at AERA, and I will be moderating today's event with my colleague, Rob Monroe.
Hey everyone, Rob Monroe here. I look after membership and technical development at AERA, and like Amanda mentioned, we're here to help you. So there's just a few little housekeeping slides to go through here real quick before we bring Cass on. A couple things. If we've got our Engine Professional podcast. So Steve and Fox and Chuck Lynch, they're techs here at AERA, and they have episode number 7 already ready to go, and it's right there on our website. If you just click into that web address there, you can watch the podcast. Episode number 7, we brought on Dave Hagen. So Dave is our senior tech specialist at AERA, and Dave is our diesel guy. So Dave is all things knowing with the diesels, and that's what this podcast is all about. This particular one is they cover all things relating to diesel, and they cover lots of ground on that. So I'd encourage you to go check that out. The other thing we got is if you've just got a new hire possibly in the shop and you're looking for some training, or maybe you're looking at updating your skills, we've got our Engine Machinist online training program. So the training program, we give you 1 year to complete it, and it's only $150, and it really is worth. You get the book, it's all online. When you're finished, you get your cylinder head machinist as well as your engine machinist certification. So one thing to check out there, and have a look at that. Another thing that we've got our AERA balancing manual, and this is brand new for 2021. There's over 100 pages of the manual there, and it covers all things related to balancing. There's balancing theory, how to set up bob weights. There's turbo balancing in there. Over 100 pages. There's lots of color photos. Even if you don't have a balancer in the shop, this manual, it really does cover all things related to balancing, and there's some really good information in there. It's just one of the advantages of being an AERA member, because as a member, you do get a copy of this manual. So if you're not a member, pretty good reason to join AERA to get a hold of that manual, as well as we do have it for sale if you are looking for that one. So again, the manual's a great resource there. So. All right, well, enough talk for me. What we're going to do, we're going to bring Cass on. Cass Choate, he's from Choate Engineering Performance. Cass he's got a well-known shop sort of in the Tennessee area. Cass is our guy as far as Powerstroke. I mean, all things related to Powerstroke engines, Cass is definitely very, very knowledgeable. We always use him on the tech line. We try to bounce ideas off of him and get his information from him. So very lucky to have Cass with us today. It's a real treat. Cass is a super busy guy. I know he's got a whole bunch of irons in the fire right now. He's got a shop. They're just expanding a really large facility that they're moving into, and it sounds like they're going to be ready to go next week. So what I'll do is I'll pass it over to Cass. So, hey, Cass, how's it going today?
Hey, Rob. It's going great. Happy to be here, and thanks for having us on. Anyway, so we are going to be talking today about the 6.7 failures and fixes. And you're absolutely right. It has been, and I apologize, I've been a little bit difficult to get hold of. It is a very, very busy week for us. We have actually got, we've got the governor coming in for a big announcement for this next project that we're moving into, a lot larger facility. And so this week is definitely been a push, and next week will be as well, so we'll be glad to be done with that. But extremely happy and pleased that y'all have asked us to be part of this webinar. So with that said, I guess we'll go ahead. We've got a lot of ground to cover, and I want to get going as quick as we can, because there's a whole lot of things that I want to talk about. I want to make sure that hopefully y'all can see my screen there. If Rob, if you can just confirm that for me. Make sure that's up.
Okay, yeah, looks good, Cass. Looks really good.
Good. So anyway, so what we want to do, I kind of wish I knew exactly who the crowd that we're talking to today. I wish I knew who we're talking to. How many are machinists? How many are maybe shop owners and mechanics, or whatever it might be? I don't know if they have a raise hand function, but it'd be interesting for me just to know, so that next time if we do anything else on this, I can kind of cater the webinar towards the audience But that said, I want to go ahead, with the 6.7 Powerstroke engine. It was first introduced in 2011, and of course, it came off the heels of a failing relationship between International and Ford Motor Company. Of course, the 6.0 failures were only surpassed by the engine following it, the succeeding engine, which would be the 6.4 liter, and it led to Ford to do something that it had never done before. And that was the first time ever that Ford would actually build its own diesel engine in-house. And so the obvious theme and the reason why I kind of want to set the tone to what we're fixing to get into is because it's important to note and understand what was kind of going through the mind of the engineer. And you can see this all through this engine. It's very apparent. Previously, the successor to this engine was the 7.3, the 6.0, the 6.4. And when they came along to build this engine, like I said, it was fully built in-house and designed completely by Ford. So there's an obvious theme for the 6.7 engine. And first is to design around the known failures of the previous platform, which obviously left a lot to be desired from the factory. But secondly, it was to design a truly automotive light-duty diesel application engine. And this meant weight was a major priority, as well as throttle response, volume of engine operations, fuel economy, weight. And again, I cannot express weight is the driving factor for the way this engine was designed. I know that we want to talk about failures and fixes, and we can limit that to the long block, but really to truly understand this engine, you really need to take it as a whole. And systems are an engine operates off of a system. There's no individual component that really is isolated. And as a machinist, you know this very well. One tolerance changes. There's such thing as stack up tolerances. There's things that everything is affected by something else. So that being said, I really need to incorporate the entire engine, and that includes some of the bolt-on things. So we're going to start from, in terms of the engine, we're going to start from top to bottom. But to kind of back up just a minute, Ford knew that this was going to be a long-term platform for them, and obviously, currently, it's still in production today. It's outlasted the holy grail and beloved of all Powerstroke, owners, and the great contender that's known as the dinosaur. It's a legendary 7.3 direct injection engine, and of course, its tenure was from 94.5 to 03, and here it is, 2021, 10 years into production. The 6.7 is still being manufactured today. However, there has been, and let me say that there's been more changes with this engine than there ever has been with any other Powerstroke platform. And there's a tremendous amount of changes, not just with the long block, but as we get into it, you're going to start seeing some of these. And some of these, honestly, I was unaware of. But being that I get to see this engine in many different lights, I'm actually involved in the company through, originally I was a tech and working on the 6.7 Powerstrokes. I see a lot of stuff that would come in for failure. The guys from Teardown, that really, really helps. I think I was talking to my good buddy, John Callies, and he was talking about how he really was encouraging the guys over there at GM to take a look at the engines as they're coming in, the failures of those engines. Sometimes there's things that you can look at under a microscope, and that's fantastic, and you want to do that, but you really get a great indication of what's going on after you've seen things after it's got 100,000 miles on it. So Teardown is sometimes one of the best areas to really get a good look at what the problems with these engines are. And I think that people don't spend enough time over there. You get busy boring blocks and getting stuff out the door. But fortunately with us, we deal with specific platforms. And because of that, it makes it a lot easier for me to kind of look and see, where we're seeing these problems. So, the 7.3 from 2003 to 2011, it went from the 7.3 to the 6.0 to the 6.4, and now the 6.7. And it's been difficult because nailing down a platform and eliminating its insufficiencies obviously takes time. And with the EPA standards and everything, it's caused them to have to change quite a bit on the platform. And it's a very unique platform to start with. And I know I'm giving a lot of intro to this thing, but there's a good reason why. This engine really deserves it. How many reverse flow engines in the light duty diesel market do you know of right now? None. And that's one thing that's really interesting about this. But there's specific reasons that the engineers opted to do what was, unthinkable before. Nobody had done it before. So the intent was to reduce the amount of pressure drop and heat loss into the compressor housing of the turbo. Because remember what we said, the big thing that the engineers were looking for is they were looking for something with good throttle response. This isn't the old days of, if you remember the old Oldsmobile diesel engine that, indirect injection and laggy, no turbocharger. And then when they did, at later date, the 6.2s, they didn't have an intercooler. And there was just a lot of things about those engines that were just very undesirable. But Ford took all that into account when they did this, and they moved the exhaust to the inside of the engine. So as you can see on the screen, this breakdown here, you're actually seeing that on the outer point right here, the valve cover actually is part of the intake. It's integrated as the intake, which many of you probably, most of you know all this. But by moving the exhaust to the inside of the engine, they're able to shorten the distance from the exit of the port to the entrance of the turbo. And we know from combined gas law that there's a direct correlation between heat and pressure. So we can spin the turbine a lot faster. We can reduce that spool up. We can use that heat efficiently if we were able to do this. So that being said, that's going to get us to our first benchmark. So what we want to look at is the turbocharger, and that is a lot of problem with that engine. So this is they call this a scorpion engine. There's a reason why, because if you look at the downpipe that's coming off that engine, and I think in the last slide it shows it a little bit better. Yeah, right here. I don't know if you can see my mouse or not, but anyways, right there on the back, the downpipe, they call that the Cobra head, but it's nicknamed the Scorpion engine. And this is the idea that we're talking about with the reverse flow engine with the exhaust ports now on the inside of the engine. It allows for a lot less pressure drop, and it allows for that heat to enter the turbine side of the turbocharger and allow it to spin a lot faster. So the turbocharger was actually the first year from 11 to 14, they kept the same turbo design, which was an SST or single sequential turbo. On the screen, if you look real close, you'll see that the compressor wheel has like if you were to mate two compressor wheels back to back, there's two inlets for that compressor. That had not been done on a diesel application before. This was all new. And the SST was a great design for quick spool up. It had, like I said, two entries, and it had not been done before for the light duty pickup market. Now, that being said, you kind of start seeing a pattern here. Ford is extremely aggressive in their diesel market, and because of that, Ford is the first to be on the scene. If you want to see if you want to see who'll be the first to do something, look at Ford. I mean, whether you're a Cummins, Powerstroke, or Duramax guy, you can't argue the fact that out of all three, the most innovative truly is Ford, and because they're the first on the scene with everything. And somebody says, well, if you need proof of that, the first variable geometry turbo was Ford in 03 in the 6.0, and the first factory built dual sequential turbo that was ever found in a pickup truck was Ford in the 6.4. The first aftercooler to be used was Ford. The first SST turbo to be used was Ford. The first steel piston to be used, check out the 2020 6.7s, it's Ford. The first CGI Block to be used, it was Ford. The first injection pressure to ever reach 36,000 PSI is Ford. So, whether you hate them or you like them or whatever, you got to say, if you want to see something quirky, if you want to see who's kind of at the leading edge of this stuff, guess who followed, Ford on that VGT turbo? Everybody. Cummins did it with the 6.7 and, of course, the LOY with the Duramax. So now that you're formally introduced to the engine, we start, like I said, we'll go back and we'll start looking at this thing. So the turbocharger was a big problem. It was great because it had quick spool up characteristics, and it had a smaller turbine wheel. It did use that SST design, and I'm telling you all this because I can only imagine that I'm talking to a lot of guys that are building engines for, they're selling engines or they're machining engines for guys, and they're building these engines. These GT32 turbos, I know this from personal experience. Horror story. Okay, we're just going to input here. Just sick to your stomach. It seems like Murphy's Law always creeps in anytime, anywhere, and especially with me. He's made a home, and he's got his own P.O. box here sometimes, it seems like. But I'm driving down the road on a test drive on a vehicle for a customer. This was back in the days of my tech stuff. I'm just driving around just to it was routine maintenance deal. And this is on a 2011 Ford F-250 pickup, cruising at 55 miles an hour. And if there was ever a Jack in the Box story, this thing popped open on me. As I'm cruising down and I'm not accelerating hard, the turbo decides that it wants to come apart. All of a sudden, it's not giving any warning shots of anything. Now, under most vehicles, it wouldn't have made any difference. The turbo comes apart. Yeah, you're going to have to call the customer and say, yeah, the turbo failed on a test drive. It's probably not going to believe you, but it gets worse. So this engine actually uses an aftercooler, and the aftercooler on the engine is a lot less restrictive than that of an intercooler. The problem with it is when this thing grenaded, it literally blew shrapnel for the entire engine and took the guy's engine out on a test drive that I'm doing just a routine maintenance on. Guess who got to buy the guy an engine? Because I mean, how are you going to explain that? There's just no way around it. So I tell you that because if you're rebuilding these engines, you want to make sure that you have, you're going to have I guarantee you're going to have this phone call. The guy's going to call you up and tell you, hey, my truck's smoking now. You put this, you built this engine or you machined it or whatever. And I notice that when I'm accelerating or I let off the accelerator that I'm seeing white smoke come out of the tailpipe. Well, instantly he's going to try to blame you for, it's just the nature of the beast sometimes that you deal with. One of the big problems is the guys that are running these turbochargers have oversped them, and they've had bearing failure, which leads to, or bearing wear, which typically leads to seals start to leak at that point because it's beyond the run out and the bearing shaft play. So you let off the accelerator, and now you have this vacuum that's on the seal side that it starts pulling in oil, and you see white smoke coming out the tailpipe. It has nothing to do with the engine that you built the guy, but it will get you a phone call, and you need to know not to go into full-blown panic mode. Somebody didn't break a ring or somebody didn't hone something right. You need to know, hey, you need to check your turbo shaft play. So that's one of those things that you and I'm telling you this on the turbocharger side, and I realize that this is Automotive Engine Rebuilders Association, but unfortunately, as this industry has grown, you're not working on the 350 Chevrolets necessarily anymore. Some of these things get complex, which mean we really need to start thinking as a system, not just as a long block itself. So that being said, you also want to know that this was also the first year that the aluminum heads were manufactured for the Ford engine itself. There's another common problem with these. These are subtle things that we're going to talk about today. And the only reason why you possibly know about some of this stuff is you just live, breathe this engine and this platform. Now, if you look at this, there is a difference in your rocker arms, and it's subtle. And Ford is very sneaky. I say that, and I'm a huge Ford fan. I love the platforms that they came out with. I like stuff that's built Ford's tough with aftermarket stuff. That's kind of my thing. But I like it after the aftermarket's gotten done with it, after we've been able to do some things with it. But they're real sneaky because they keep part numbers the same, and they change some of the engineering part numbers. Now, you can tell the difference between an engineering part number and an actual part number from the guy across the counter, simply because the Q indicates that in the prefix. Now, this rocker arm was a problem. The reason why this rocker arm was a problem was because, let's say you are at idle, and this happens at idle. And the reason why it happens at idle is because you've got, obviously, lash adjusters, hydraulic lash adjusters. And those lash adjusters, let me see, I'm going to scroll down here on this other screen and see. The lash adjusters do not have as much hydraulic pressure against them. And at idle, you notice this thing starts to miss like crazy. And you pull your valve cover off and you find out there's a push rod that's just laying over there for no reason. And you're going, what in the world? Why did this happen? Well, here's the difference. Ford never came out and told you about this update, but I'm telling you about it now, that it uses the same part number, but it is a totally different rocker arm. If you know the difference, and let me back up that screen. And again, I know that we've only got like 45 minutes to show, but if you look real hard, you can actually tell right here and identify it pretty quick. If you look at the one on the right, you can see that it's got a lot more shape to it. This one over here is more of a kind of a single plane. It's more straight. That's the quick test to find out. If you wanted to know exactly what the difference is, you can take a micrometer or a caliper and measure this, and you'll actually see, I think it's about, I don't know, if you look at it, it's around 140 thousandths roughly difference. They extended this little leg right here. They actually extended it out to keep that rocker arm from falling off. And again, you'll only see this happen at idle. because as you get a little bit of lower, at full operating temperature, your oil pressure is going to be a little lower, and you're going to see that the slack adjuster or the push rod itself, the tension there between the lifter and the rocker arm becomes to be a little bit greater. So that is something to look out for. Now, one of the biggest issues that we have seen on the 6.7 Powerstroke failures is undoubtedly and if you're in it very long, you'll see this. This is, the valve failure and the cylinder head failure. I'm going to touch on this cracked head on the passenger side, and it is on earlier 11 and 12 models, and they can crack for no reason. Sometimes they're more prevalent to crack after multiple torquing, use of ARP studs. If it were me, I wouldn't gamble with it. I would just go ahead and replace it with a later casting. I've got more things to cause me problems in this life, and I would rather just, fix it and be done with it. But in the picture, you can actually see where it's kind of steam clean. And typically on that third cylinder back, which that's also something that I need to note. The numbering of the cylinders changed because the manufacturer of the engine changed. Used to, it was 1357 on the passenger side, 2468 on the driver's side. However, that's changed because Ford Motor Company numbers their cylinders different. It's 1234 on the passenger side, 5678 on the driver's side, which is important to note because if you ever come in with a bad injector or low compression on the cylinder, whatever the case may be, you definitely want to make sure that you don't misdiagnose that and replace the wrong injector. Cracking in the cylinder heads is definitely on the earlier models. Again, one of those things that were definitely more common. Moving along is the valves. That is the #1 cause of failure for the earlier year model vehicles. Valve failure was prevalent. They just did not figure, again, that the big issue that Ford had was they didn't fully anticipate. First off, it was an inferior material that they were using for exhaust valves. And when this thing first came out and they were having all these problems, they actually were, they put out a technical support bulletin. And the technical support bulletin, originally they thought that it was the glow plugs that were breaking off causing the problem. And they started changing glow plugs. And it didn't take them very long into investigating to find that the valves are actually splitting. And they're, again, splitting because inferior material was used, but also keep in mind that now they changed an after treatment system that used to be more along the lines like on the 6.4. We were using a DPF system, true enough, but it was through the 7th and 8th cylinder on the exhaust stroke that we were introducing the catalyst for the burn to lower hydrogen, we were using it to lower our emissions. So what they've done here is they introduced the use of diesel exhaust fluid. And because of that, there are temperatures reaching in that in the DPF 1700 degrees. You're taking all that heat, you're backing it up into the turbo, you're backing up into the exhaust valves, and it gets to be too much for the exhaust valves specifically. They were more of a problem than anything else. But again, it was such a problem with the with Ford that they actually had a TSB that came out that said if you have low compression on this a cylinder and you've also got this certain glow plug fault code, don't go any further. Don't try to diagnose it. Just go ahead and replace the engine. So you went from 0 to 60 in a split second. So that was pretty interesting to see. Something else that they did, and I don't know that I've got a slide for it. Well, I do have one here. It's not exactly a great picture for this, but maybe you can look at the other one over here. Of course, this is the effects of the failed exhaust valve. And we see what happened when that happens. It's just obviously catastrophic failure. But they did change piston design, and instead of using the previous design of a reentrant bowl that they had a lot of problems with, Ford really had a second time at bat because they saw the failures of the 6.0s, they saw the failures of the 6.4s, and they go, we don't want any part of that. We definitely want to make sure that whenever we do this, that we address all the problems that we can see. One other thing that I missed, you know, we make a 6.4 engine that we're kind of known for, and one of the things we designed, I think I mentioned on the last time through, was that we have integrated oiling system on the valve covers. And what I basically did, and I just finished doing a redesign on that because I came up with an even the way that I like even better to apply the oil to the rockers. But I took that design and I basically went and grabbed the 7.3 and I grabbed the 6.7 idea and I made it for the 6.4. Sometimes you don't have to reinvent the wheel, you just reinvent the application. But the 6.7 was the first to use that oiling rocker system. Now, they've never done that on any engine before, on the diesel market anyway, but that I'm aware of. I know I can tell you for a fact it never happened in the diesel market, but it was interesting to note that they really did their homework with the previous failures. That being said, they were going to address everything. They knew that was a problem with the 6.4, so they added that oiling system. But they did the pistons with a completely different design that was very similar to the Cummins guys. We saw that design on the early 03s. Cummins got away from that. They changed their piston bowl design and found out that they were actually having ring compaction and wall infringement with the other bowl that they had designed. Then they went back to the similar bowl that Ford uses now, but Cummins was using it before then. So there also was a big change, and that was with the lifters. So it's a dual lash adjuster. It's a bore of about 1 inch, 172 roughly, and that was completely different. So they used it's right at the wheel on that lifter's 1 inch 50 thousandths roughly. But anyways, it's a much larger wheel. Some of the reasons why they felt that they needed to was to, in their attempt to be able to reduce some of the wheel speed and some of that load on the rollers for the needle bearings. And they saw a lot of failures with the 6 liter. Now, that being said, and I told John Callies, he said, you know, I'm going to be listening. I've signed up for your webinar, and I told him, I said, I hope that you lose power at your house, because man, I'll tell you, it's like knowing that Sandy Koufax is watching you in Little League. But and he is definitely the lifter guy, and with Morel lifters, he knows, he's forgotten more than I'll ever know. But and he could expound more on this. But one of the things that we see is a lot more lifter failure with a 6 liter than with a 6.4. And I think that's pretty obvious, the reason why. And the big reason why is it uses a hydraulically actuated, electronically controlled unit injector. What that means is obviously the oil pressure is the catalyst for the intensifier piston in the injector, and that's what creates high pressure fuel. Now, all that compressing and shearing, it takes place, a lot of heat generates, and the heat, I see more causes of failures with lifters with high oil temperatures. Guys that have ran oil coolers and they're running a plugged oil cooler or something like that. So Ford did that, and they beefed up that lifter. I do see failures in these. The reason for the failure is it's not that often that we see the failures, but the cam grind itself has some interesting. It's an interesting grind that they have on that, and there is a certain area in that lobe that we're seeing skidding across. Also, it ramps on that lobe. It's actually, the transition is pretty harsh, and some of that, the impact and the harmonics that are being introduced are what's causing the premature failure of that. Now, moving along there, we're going to get into the block itself. And again, I mean, I'm going as quick as I can on this, but there's a ton that I'm leaving. This is a Cgi Block. This is something interesting to note. I know a lot of guys in the machining world are going to ask how to treat, how are you going to machine this? Because with a Cgi Block, your approach to it needs to be a little bit different than that of a typical gray iron. There's some different characteristics in Cgi that there are in, obviously, in gray iron. Cgi is a lot lighter. It is 50%, 30 to 50% actually more durable. It has got a lot greater resistance to wear, and that is no doubt a big improvement over the previous engines that we've seen. Now, the thing about CGI is that the Brinell hardness of a compacted graphite iron block is 217 to 241, whereas a gray iron block is about 179 to 202. And ductile iron is 217 to 255 on the Brinell scale. So it machines very much like ductile iron would. So your tool life is going to be 10 to 20 times lower, according to some of the studies that I've looked at. And feeds and speeds need to really, you know, if you're not doing a lot of this, you're not doing high production, you can treat it and you can get by as such with very little changes. But one thing to keep in mind is when it machines like ductile iron, I don't know how many of you guys use LA sleeves or something like that when you're doing this blocks. It's a really, really, really hard sleeve, and we know that we have to slow our feeds down, and our processes get a little bit slower. There's, you know, your tool manufacturer is going to be the one to talk to because that's going to vary. You know, with typical carbide tooling, a lot of that has to vary with the tool that you're using. So if you are set up with MSC or Machine Tool Services or whoever you get your inserts from, those are the professionals. Those are the guys that I would definitely talk to about it. One thing, and this is, I'm interjecting this as my opinion. I noticed that the dampening characteristics of CGI versus gray iron is a ratio of about 0.35 to 1. It does not have the same dampening characteristics that gray iron does, and for that reason, I believe that fly cutting, you tend to see more waviness, and I think that there's an introduced harmonic there because the block does not have the dampening effect. It's a lot easier to machine something in a rigid setup that does not have that, you know, when you start introducing a harmonic to something, then you start introducing chatter to it. And because of that, you know, I had called one of the contacts for material with CGI. He's a professional that was referred to me, and he had said that they were actually changing their setup and increasing clamping loads on the CGI when they were manufacturing and when they were machining it. Now, to what extent, you know, there was no quantitative values given or anything like that, so I can't tell you. I just know from personal experience that, again, I'm seeing a little bit, we're fighting more of surface finish, specifically when you're decking blocks and things like that, not so much necessarily in honing. When you're honing, you're going to still, you know, the same standards that you're using. And if you're not using a profilometer, you need to find one and get one. But RBK, RPK, RK standards are going to range like an RPK, typically a 10 to 20, RK, anywhere from 40 to 60. And again, this is going to be based on the guy's application. Guys that are running and Lake Speed and Keith Jones and Ed Keebler, they've done a fantastic job of educating the crowd on that. I'm not going to be that horse, but they know there's a lot of good information out there from them. But RBK numbers are definitely going to be dictated by the application, higher boost pressures and things of that nature. So, but you're going to treat it very much like the same finishes that you would in any other. Now, there's one other big thing. Well, there's a lot of other big things, but the next one's fine. Is going to be, this is a difference in connecting rods. I'm really concerned about some of the stuff that Ford does and I'm not trying to pick on anybody, and if there's anybody out there with any ties to it, please, it's not that. This is just, it is speaking to guys in the field, like myself and like many of you listening. These are things that you need to know about, things that you really need to think about. And one of them is the fact that there are so many changes with a 6.7 Powerstroke engine that they haven't supported it with other things. And I'll tell you what I mean in just a minute. There's been a big difference in the rod changes. There's actually 4 different connecting rods. Most people will go, well, no, I only know of 3 of them. Yeah, that's true. There's a 34 millimeter that they started out with. Now on the left side, that's the older version rod. That was again, going back to what was the theme of this engine. The theme of the engine was, if we can lighten this rotational assembly up and we can put a turbocharger on it that will spool, we can make this thing drive like a gas burner. I mean, take off the line really quick. We're going to reduce all that engine lag and throttle response. So they go through and they start lightening this thing up and they start hacking away at the rotational assembly. and they find out that it's still a diesel engine, and your pressure rise on a diesel engine is much greater than that of a gas burner. You know, you can have per crank angle 50 psi per crank angle in some diesel applications, 10 to 20 maybe on a gas burner. But that is a major issue when you start getting into rotational assembly and the rigidity or the mass of it. It has to be able to support those higher injection or those higher cylinder pressures. And because of that, they decided in 2017 that, yeah, we messed up. We probably ought to go back. We're bending too many connecting rods. As you see, the one on the left is pretty pathetic. You should be ashamed of yourself. If there's any engineers here from Ford, you should be ashamed of yourself. You should have never put that in a diesel application. It didn't belong. So in 17 again, what they did was, now I told you there's 4 different rods. Now that's true. You've got a 34 millimeter rod. You've got which we refer to as, and this is a technical term for it, the one on the left, it's the dinky rod. Okay, so the dinky rod actually had a 34 millimeter wrist pin, and then they actually put a 35 millimeter wrist pin on it. And then they go, you know what, that's a transition from, I believe, 16 to 17. And then they scrap that. They go, you know what, we're going to come out with a whole other connecting rod. So they did that. And that's the one you see on the right-hand side. Now, something to note. What you see in front of you is, unfortunately, there is one of these that are missing, and I did not happen to have that rod in stock. So I tried to do a little bit of work for you so that you could see. Now we have on the right side, excuse me, I think the left side, you can see there's a tremendous amount of difference in the rotational assembly. The one in the middle obviously is a steel piston. It uses a different center to center. It uses a steel piston for the 2020s. They redid the connecting rod. It's a lot more, like I say, a lot more robust. There's a difference between the 11 to 15 rods in the weight. There's a difference between the 15 to 6, the 16 to 17 rods in weight. And when they came out with the 17 rods, and they kept that till 2019, they're 8 grams heavier per rod. I know you can't see that here, but they're 8 grams heavier. Here's my problem with that. You did all that, and then you're going to support one part number for the flywheel and for the harmonic balancer. What really, kind of scares me about that is the fact that the guy, if he decides that he rips a flex plate out. Now, mind you, the flex plate on these things, the first time we ever got flex plates, I think Chuck Lynch came down and we were talking about that the other day. Said, the first time we ever got flex plates in for these engines, we sent it back 3 times. This true story. We sent it back 3 times. We go, you gave us this. I don't know if this came out of what gas burner this thing came out of, but this is not the right flex plate. They actually changed those flex plates from 2011. They used an 8 lug, 2000, and that split. I mean, I've got it in my notes somewhere, but I think it was roughly November 8th, 9th, somewhere in there. They split that and they started coming out with the 6 lug harmonic balancer. When they did that, the flex plate changed. And again, they lighten this thing up. I mean, they keep taking weight off this thing. And from every angle, aluminum heads, compacted graphite block, rotational assembly, harmonic balancer, you name it, they're shaving weight on this thing ridiculous in a massive way. But they're using the same flex plate for a 2021 for a 2011. There is no difference in part number. The problem with that, I see, is that you have a connecting rod rotational assembly here for the 2020. The connecting rod, the piston, everything, we're seeing a difference. I mean, there's a variation right here that I'm looking at least 80 grams. That's a big problem when you go to slapping something on that didn't exist on an older engine. Now, it's not so big of a problem because here's another thing that I've got against, and I know but we are talking about failures and fixes. So there's one more thing that I've got against Ford. When they're putting these flex plates on, what they're doing is they are more concerned, and they're only concerned about the current engine they're manufacturing. As far as, and we've seen this in other OEs, but as far as support that's given, that how this is going to affect the engines that were made previously, it's not really a major priority, which means that let's say the guy rips a flex plate out of his 2011, or let's say 2012 or 2013. He grabs this flex plate. The weights and everything have been actually designed and moved around. The actual weights, counterweights and everything were for the 2020. And then you slap it on this other engine. What's going to be the effect of that? And how far out of balance are you going to actually be dealing with that? That's a big issue. Now, that being said, that reminds me of something else. If you, and I have a lot of customers that ask me this too, and I can't see your faces. I hope you're not all asleep by now, but if you do, or you are, I don't blame you. There is a big deal, a big problem that I see on the new, let's say you bought a new block from Ford, okay? Let's say that you're buying this block and you only need the block, or let's say you buy a new block from them and you tell them it's for 2014. I don't know if they're going to transition away from that, but currently they're not. What they're doing is they're machining that block. Now, we said that there was a steel piston there, right? Well, the expansion rate of steel and the expansion rate of aluminum are completely different. Anybody that's been a machinist for 5 minutes can tell you that. Problem with it is your piston wall clearance needs to be to accommodate that piston, whether it's aluminum or it's a steel piston. Problem with it is they're not doing that. They're machining it for one diameter, for one piston. Guess which one? Yeah, the steel piston. They're not really worried about you if you're, running a cast aluminum piston. That means that you are running now about 1 thou to 1.5 thou piston to wall clearance on an aluminum piston. There's a problem with that. It doesn't work. It doesn't work very well, and it certainly doesn't work very well if the guy winds up putting a tuner on it or anything else. Boosted applications with a cast aluminum piston, I really would want to see, 3 thou piston to wall clearance on, given that bore size and everything. It's typically what I'm going to run. So that's something to keep an eye out for. And again, you're starting to see the theme. The theme is this: Ford is making all the new stuff, but they're not supporting the old stuff. And there has been such a huge difference in the design changes of this engine that it doesn't cross over. It'll bolt on, no problem, but that's where it begins and that's where it ends. All right, so moving along from there. Okay, so yeah, this gives you an idea. This is the dinky rod has met its match and it is bent. So this was the upgrade to the 2017. This rod below on the very bottom is out of a 6-liter. So you can start seeing kind of the transition where they met the happy medium. They're still trying to, reduce weight, and they're giving up a little bit of that. They're going to go ahead and concede and put some more meat in the rod and make it look a little bit more like a 6.0 rod. So from there, the next thing that we see, and we see this a ton. I see that the time is 12:46 now, and I'm trying to hustle as much as I can. Again, there's a lot of material to cover. One of the big things that we see, and we see this a lot, trying to get good cores has been a big problem with the earlier year models. Spun bearings, and they are spinning them left and right. Some guys will argue with you and tell you there's absolutely nothing wrong with the way that it is. I can run a 1540 oil in this thing. It doesn't matter. One thing that you again need to know is that Ford, when they engineered this, they designed it with the idea of good fuel economy. Well, one of the things that they're trying to do is go with a lighter weight oil. They started tightening up the tolerances of the rod to 7/10. And we personally, when they first came out, we experienced this, and we were getting cores in. So they're going with a lot lighter weight oil. The recommendation of it is a 5-weight on, or 5W oil on the trucks, depending on the year model. I have noticed that there has been some differences on the later years where Ford now is starting to open up those clearances, and this is rod clearances and main clearances. So they are running a lot tighter clearance, but that's only one of the big issues. Another big issue is that your customer is a diesel guy. Papa's tractor and, grandpa's old, 89 12 valve ran fine on, maybe a 15W oil, which was fine, but his clearances were about 3.5 times more than your clearances. There is, Lake is, and Keith are always talking about the R's of oil, the right amount, the right place, the right time. you can't achieve that when you're trying to compress this oil through a clearance, and it's the pour point of the oil is it starts to infringe upon that when you take this heavy oil that you are using in a very cold climate. The oil is not going to move as it should. There's another problem, and we just keep adding more problems to this. The other problem is the way that they pipe this plumbing on this thing. If you've looked at the plumbing on it, and again, I apologize. Wait a minute, I might have something. This is the oil pan without the pickup tube of I can tell that this is 2017 oil pan. They had a lot of problems with the upper oil pans leaking. They did away with the gasket and they started using an adhesive. Anyways, the oil goes from the pickup tube into the, obviously in the front cover where it's compressed from the oil pump. It goes down into this cavity here out of the block, goes all the way down, it actually goes through a oil cooler, which again, that is one more thing that they decided that they can make better because of the location. If it had to be replaced, I'd much rather replace one of these than I would a 6.4. And then it goes from there across, it shoots across the block, and then it goes through the oil filter. Then once it goes through the oil filter, it goes up the side of the block. And then after it goes up the side of the block, it decides it's going to go through the cam, and it feeds that galley on that side. It's a hollow cam, which then it crosses back over the other side of the block. So we've zigzagged now twice. That's a problem because we're piping oil from 20 miles away, and we're trying to feed this thing with an oil that's actually the viscosity is way too heavy. The clearances are way too tight, and the distance from the oil pump is way too far. And you can imagine that is a perfect storm for a spun bearing. So we had so many problems with that. We started paying attention to where these cores were coming from and what the failures were. One thing that we didn't note was the fact that the cores that we were getting from up north were more prone to spun rod and spun bearing failures. At least that's what our library and our data showed, because we track that stuff, and I'm trying to get better about making sure we know it's really useful information. I'm very much I love watching Columbo and some of the older detective stuff. That's what you're doing. I mean, when you're engine building, you're a detective and you're trying to figure out, okay, don't contaminate the crime scene. I need all the evidence. I mean, everything, things that you didn't even think were important, where you live. There was an interesting, and this is too interesting to tell. I don't know where I may have been an ARA article. I don't remember, but I thought what was really funny one time was there was back in the 60s, there was a guy that wrote an article into GM or Pontiac, I forget, and he said, my car is having problems. My car will only have problems if I stop for ice cream and ask for vanilla. And every day when I go and I get ice cream, I shut the car off, it won't start back. But it's only if I get vanilla ice cream. If I get chocolate ice cream, I don't have that problem. And it was such a ridiculous, letter. They thought they were going to go out and they actually sent an engineer to find out, what in the world, is this guy just crazy? Is there any validity to what he's saying? Obviously, the car doesn't care what kind of ice cream or you got ice. What is he talking about? Well, they did. They drove around, and the guy goes to the car hop that he was used to going to, and he gets chocolate ice cream, cranks the car back up, and he drives off with the engineer. He said, I told you I wouldn't have that problem. He said, okay, well, wait a minute. Let's go back and let's see what you're dealing with. So he goes back, and sure enough, he orders vanilla ice cream. And the guy goes to get the vanilla ice cream, brings it back, car won't start. It actually, vapor locked. And so he's going, wait a minute, hang on. It doesn't have anything to do with the ice cream. What it is that the store actually put the ice cream in the very back for vanilla, and the amount of time the car had to remain off was longer to get the vanilla ice cream than it was the chocolate. So was he telling the truth about it? Well, yeah, but there's a little more to the story. The thing is that I tell that story to say you really need to be looking as a detective and seeing everything that's laid out before you. So again, that's the more information you can get, the better you're going to be at this. So this picture here that you see is where you have a very large volume. You have a very large galley, There's another issue with pressure drop because they're increasing volume, but you do have a pressure drop with that galley across that oil pan. So again, like I said, it was just a perfect storm for spun bearings. I'll try to kind of move along as quick as we can. Obviously, broken cranks were more of a problem on the earlier year models than the later year models. Why? Some folks said that it was a heat treating issue and it was this, that, and the other. The truth of the matter, at least from my experience, I'll tell you, it has nothing to do with the heat treating of the crankshaft that I actually saw so much of a problem. And sometimes if you watch the OE and you find out what did they actually do, then you can see they knew about the problem. They just didn't tell you about it, and they kept the part number the same. If you look and you pay much attention to part numbers, you'll see that 2011, 2015, again, what did they do? They lightened the rotational assembly up. Why? Better throttle response, better fuel mileage, all the other things. They had noticed that there was not enough mass, rotating mass, for the harmonic balancer to be able to absorb the order of imbalances that was created through, obviously, combustion. So they came out with a much more robust crankshaft dampener. And because of that, that really has eliminated, all but eliminated the issues that we saw. Other issues that we've seen, 32 bent push rods. Why? Because the crank gear spins and it winds up creating all those problems. Obviously, the valves are still open when the piston comes up. Something else to note, and I just included this because it's important to note all of the different problems in the areas that they had. And again, when it goes back to me telling you about, I get the opportunity to work on the vehicle, I get the opportunity to see the stuff in teardown, I get the opportunity to machine the block, to cut it open, to look at the ports, to look at the water jackets, to see where the failures are on stuff, and then get to look up. Sometimes it's really a good idea to spend some time actually looking up your own part numbers. I know a lot of guys are busy and they got their own parts guy. The problem with it is sometimes that the parts guy, you don't pay that much attention to, okay, when did they make that change in that part number? Why did they make that change in that part number? It cost them thousands, millions of dollars to change parts. They don't do it for no reason. The OE is not ignorant. They know what they're doing on that, and there's a reason why. And sometimes there's a good reason that you need to know, but you're not going to know about it unless you've done the actual homework and found out what was the cause of it. But upper oil pans are definitely known for leaking on that. There's a lot of torsional load because that upper oil pan also is your bell housing and your rear cover adapter. It's all integrated. The lower half of that's integrated. And because of that torsional twisting nature, you tend to develop leaks. The gaskets start to, over time, start to lose their elasticity or whatever you'd like to call it. They start to flatten out and they can create leaks there. So Ford actually did away with the old style gasket and started using just an adhesive. So that's just kind of like I say, that's a 20,000 foot panoramic view of some of the problems on these engines. I know that I've skimmed through this as quickly as possible, and I'm sure I've left out some more things. There's a lot more to go through on this engine, and we're working on a lot of aftermarket products. That's one that was actually going out today. That we've got a lot of things from anywhere from, depending on the model that you purchase from us, it comes with certain things, billet flex plates. It comes with a bunch of different things that address those problems. We machine the problems out of the block that we can, and those problems that we can't machine out of the block, we manufacture parts to fix that. So I hope that's been informative. I hope that you learned something today. I greatly appreciate Rob and AERA having us on and being able to talk about what we love, and that is diesel engines. So at this time, Rob, I'm gonna hand it back over to you.
Thanks, Cass. Really good information. I mean, everybody that's on today, I know you were really pushing for time to try and squeak it in within the hour, and it almost seems like we're going to have you back for a part 2 to this scenario, only because you get a lot of material to cover, and this helps us out so much. I mean, not only us picking on you on the tech line for the stuff that we see for the calls that are coming through, but I mean, these are real world fixes, and this is real world stuff that you're having to help solve for us. So greatly appreciated. Really good information. If you have a few minutes, I do have some questions that are coming through, and we can take some time. And everybody, just go ahead and put your questions in the questions box. We'll get them over to Cass. And again, we are trying to respect your time, but Cass is a busy guy, so if we can keep him on and try and nail down some of these questions, it'd be great. So, Cass, one of the questions that's come through is, so piston pin bushings, what are you doing with those, or are you just putting new rods in with every build?
Well, piston pin bushings, that's a good question. King makes a bushing for that. What we do is we'll press it in, and then of course we'll bore it to size and finish on it. But I don't know how much time that I would actually spend and how many that we actually do. It's not a lot, and the reason why it's not a lot is because we typically try not to use those rods that were from the 11 to 17 stuff, especially in different type builds. Like for instance, if a guy buys, we have different models. We've got a daily driver, we've got a workhorse, we've got a racing application. But those builds that a guy's really going to be pushing that engine, he's going to be hauling a lot. Those rods were just not really that desirable for obvious reasons. So we do go through a lot of new connecting rods.
Okay, all right. Another question. This gentleman's asked, he said, in another webinar that they attended, there was mention that they were finding bent push rods on the 6.7 engines, and they had traced the root cause to DEF in the fuel. They offered no explanation as to why that might be the case. They just said that they knew that it happened. Have you ever heard of this problem, and can you shed any light on why that may be the case?
One of the problems that we never even touched on, which was a horrendous issue for the 6.7, is the Cp4 failure. If you had any DEF in that fuel system at all, because the tolerances are so tight, and they have to be such because injection pressures are so high. If you had any DEF in that system, it would have shut that engine down. I certainly believe, because you're using piezoelectric injectors in the fuel system, and there's just the DEF is very thick in nature, and it's so corrosive and so destructive in nature that if any gets in the fuel system, the truck's done. It'll generate like a P0087 code, and the pump just cannot compress it to maintain fuel pressure.
All right. You had the one slide there, you were talking about the desired RPK and RK, and they're asking, what should the desired RVK for a stock build be?
Anywhere from around 50 to 55 is fine.
Okay, all right. You also had one slide there, Cass, where you were showing that the crank gear had spun and that was causing some bent pushrod issues. I know that crank gear is not indexed or keyed. What are you doing as far as, if you have to change a crank gear? Do you have special tooling made up, or how are you handling that?
No, the fact of the matter is you definitely could do that and indicate off of the hub of the crank, but it would take, like you say, special tooling to indicate off that. And the truth of the matter is right now, sometimes it gets to the point where it's worth that, but and worth the time to make up the tooling. Sometimes it's not. And it's just easier to not use that core, set it aside, and then eventually when you get enough of them in, you can afford to spend the extra time to make a jig so that you can verify the timing marks on everything. But as of right now, I haven't really sought out any tooling or desired to make any for that because of the reason of 6.7 stuff still being manufactured, and some of the parts really aren't. I think a brand new crankshaft right now is $400 or $450. Don't quote me on that. And while that does seem like a lot, it's just not. With as busy as we are on that, it's just not worth chasing it.
Okay, all right. And this question that's come up, this is one that we answer on the tech line quite often. It's not just for this engine; it's for many different platforms, but is it necessary to replace rod bolts or main bolts on the Ford 6.7 diesel?
It is a torque to yield bolt. I would highly recommend doing that. Absolutely.
All right. Here's another question we get on the tech line quite a bit too, is that they noticed main and rod bearings don't have a locating tab. Which way do they go, or how do you handle that?
Well, that's a good question, and that goes back to something else that we were talking about earlier. As far as the locating tab, we actually have a fixture that if it's something that so long as it's centered in the main bearing, the housing bore, you can actually take something as simple as you could use something like a caliper for all that matters, but you need something just to make sure that it stays center of the bore itself. We've got a little quick kind of like a go no go type gauge, that you can set over there as a fork basically that would center it, and that works well. But to answer that, and this is a different question. There's an upper and a lower bearing. One is coated. Obviously, the coating of the bearing that for the rods is the upper. But a lot of people are kind of confused about those tabs because they believe that that keeps them from spinning, and it's not. It's simply for locating. So they started to tab to pin those bearings, and that wasn't the real issue with that. I know that's kind of more than what the question was. It was more along the lines of how to locate it. So long as you have some way to center that. And you can ensure that. There is another thing that needs to be known about it. It's not so much that is a problem, because you can do it with very primitive tooling, something that would be, just like I say, that would allow, like a fork, that would allow it to stay center. The thrust bearing itself is more imperative than really anything else for that matter, because making sure that's a 3-piece bearing, which again, Ford figured out that was a problem. And they were having a single piece bearing when those single piece bearings were really, really problematic. We've seen those fail. The 3-piece bearing needs to make sure that you're preloading that crankshaft, the axial load on that crankshaft, bottom it out, and then torque it, and then check your in-shaft play. That one's the most critical. I mean, they all need to be right, but the one that you really need to be thinking about is that thrust bearing.
All right, super. Yeah, good to know. Okay, this will probably be the last question, Cass. Again, just trying to respect everybody's time. I know we've got, especially yourself, you've got a lot on the go there. So the question is, do you tighten up the crush to put more retention on the main bearings? Do you ever pin the main bearings? I think you just answered that, but that's the question we got coming through.
Yeah, I mean, just pinning the bearings is not, I mean, let's think about the problem and not, that's unfortunately kind of it's not even a Band-Aid that works, because all you're doing is just maintaining the bearing so that it can absolutely be destroyed in the place that it's at. However, the good thing about it is you don't have to pick it up out of the pan. You might be able to pick it up, when it's destroyed, out of the cap itself. It doesn't serve really any purpose.
Okay, so one more here. Do you have any suggested profilometer numbers for a performance build?
Yeah, that the RVK is definitely the number. The RVK and the RK are definitely the numbers that we're chasing. We're going to increase the RVK as we increase boost application. You're trying to blow that oil off the wall with a higher cylinder pressures. So that being said, you can increase RVK in some scenarios to as much as 90 to 100, and that's typically for. I mean, we're talking performance builds, high performance builds, where guys are seeing boost pressures that would be 5 times that of what you would normally see maybe in a stock application. So that's RK numbers can be as high as 80 in certain applications. So that's pretty extreme, though. That's not something that you're going to see a guy running on the street.
All right. Yeah, super. Well, Cass, again, we really appreciate your time. I know you're busy, and I would encourage everybody, Cass is a great guy, and he'll be more than happy to answer any questions you've got. I would encourage you to check out his website, give him a call. They've got a lot of, like he mentioned about his valve cover designs and different things that they have on the go. So a lot of different things to help improve these engines and stop them from failing. So Cass, I'll let you get on with your day. Thanks again, and it's always great to hear from you.
It's my pleasure. Thanks so much, Rob.
So right now, I'll go back over to Amanda, and what we'll do is we'll wind things up here.
And then you will see our contact information is listed there. You can reach the entire AERA team at 815-526-7600. If you have a question for our techs, you can always email the tech department at tech@aera.org. And then you will see my email address, and Rob's is there as well. If you haven't followed us on Facebook, Instagram, those are also great places to go and follow us to keep up to date on upcoming webinars and everything else we have going on here at AERA. So once again, thank you everybody for taking time out of your day. We really appreciate it, and we hope you have a great rest of your week.